Today we're gonna do a complete teardown of this Be Quiet 500 watt power supply, going into detail what are the functionalities of the different components. During this extreme teardown and repair, I'm gonna definitely point out some of the shortcomings and also the design flaws what the engineers have done during the design, of where they really saved, tried to save a couple of cents or a half a euro on particular components where they should have not tried to save money. Please, if you want to save money, then save money on the expensive packaging instead, but do not save money on the components which are really important, or they are even having vital functionality. The Be Quiet brand or company is very well known due to the very silent fans what they use in their products. And I must say that this power supply what you see here is indeed have done a very good job for me. I have bought this power supply about 6 to close to 7 years ago, out of which it was running non-stop 24/7 for about 2 years. You might remember this power supply because I put this into my new virtualization server, and I even mentioned that I should have bought a new power supply. And indeed, now I have issues that if I push the power button, then my virtualization server doesn't boot. It just gets stuck before the BIOS is being initialized. So I would think that the power supply really went bad after nearly 7 years of use and abuse from my side. I must emphasize that this video is not really meant to bash the Be Quiet as manufacturer. So this is why I edited this video and re-uploaded it again, to actually give you the right context of what this video meant to do for the viewer. Needless to say, do not do any type of teardown or repair on such electronic equipment which can kill you. And also keep in mind that just because you unplugged the unit, the capacitors inside still hold lethal voltages which are enough to kill you. To open the unit, then you just remove these 4 screws here. After you remove the 4 screws, then you can just lift this top cover in which there is the fan. And we have our first sneeze on the electronics inside this thing. I'm gonna zoom in and we're gonna check out the individual components, but yeah, that is just a general, first view of what you can expect. The cable here for the fan is rather short, so yeah, we're gonna have this thing apparently attached until I don't manage to remove this thing out of the case. Yeah, sorry for the reflection, but I cannot do anything about it. The case is really reflective. Anyway, the big trick what you can eventually learn from me is that, as you see, we always have the cabling here in these non-modular power supplies. And in order to get access to the printed circuit board and the components, somehow we need some slack, or at least we need to kind of move these cables into the side. And if you look carefully, you might be able to see that there is a slit right here in this plastic ring. So the trick is that you have to then first rotate this plastic ring, which then blocks the cables inside the metal case, such that you rotate it right here. Okay, as you see here, there is a cut in the metal. So this is the place where we can actually then remove the cabling. After you have moved this slit in this plastic ring to the side, as you see, so I can put in my screwdriver, then you should then work your way from the inner side. So you can push down these small plastic tabs, and then you can pull this whole plastic ring back and you can pull it out of this metallic frame. Here we then have this plastic ring then pulled out. And now you can then take a screwdriver, open it up, and then remove it from the cable loom. So here is then the plastic ring. And as you see now, for the cable loom, there is actually enough space so that we can pull the cables nicely out through this slit on the metal casing. And this is how then we can get the cables to cooperate. Next, then I'm gonna remove the 3 screws which are holding the printed circuit board to the bottom of this metallic case. By the way, they have been so cheap, they haven't even used the 4th screw. So right here in the corner, I cannot really show you because of an awkward angle. They are using one of these plastic standoffs instead, so they even saved a little bit of money on that thing as well, instead of using a screw. After the screws have been screwed out, then we can lift the printed circuit board out. I prefer to use this cable to hold the printed circuit board normally. And the reasons are the following: that if you put your finger in the wrong place, you might cut yourself. And also you're gonna get a pretty bad electric shock if the filter capacitor is still charged. So yeah, please be careful what you are doing. Here is then the printed circuit board. I haven't touched it yet. What I will do in the next step is to, first of all, I will check what is the voltage on this large filter capacitor here. Because that is always a good thing to test. And if there is a charge, then normally I use a large 10 watt 4.7 kilo ohm resistor, and I actually discharge the capacitors. On the filter capacitors then we have, well, practically we have nothing apparently, which is good. It means that the filter capacitor is discharged, so that we can continue on working on this thing. So the situation is that these cables, which are the mains inlet power cables, so this one going to the power switch right there, and this is the main power inlet. So those are the 2 cables, and that's the grounding wire. So these are not seated in a removable any kind of connector or something. They are directly soldered into the PCB, and they are quite short. So in the next step, I'm gonna actually desolder these with a high power soldering station, so that we have physical access to the board, because right now from the 2 metal pieces there is just no way to get to the real components themselves. Here is then the printed circuit board in all its glory after I have desoldered the power connection cables and the power switch, which actually, as I will explain you, it is not a real power switch, by the way. Anyway, so then let me do a, follow the power game of what is then happening on this power supply printed circuit board. Let me zoom in. The power comes in here through these 2 holes. So as you see, this one is the neutral wire, and right there is then the hot wire. Then the hot wire goes into a fuse, which is heat shrunk here. So there is a heat shrink tube put on the fuse itself. Not the most elegant solution, but yeah, it's gonna work. Then it goes into one of these filtering capacitors for filtering out the high, noise generated by the power supply itself when it is doing the chopping of the voltage. Then it goes into one of these filter cores. Actually, there was supposed to be 2 of these inductors, as you see on the board, but they said, no, we're not gonna put in one of these inductors and the ferrite into this power supply. Nah, we're gonna save that 20 cents. So I'm not the only cheapskate apparently. So they just pushed in a bridge, as you see here. So yeah, that is the inductor. Nice, nice. After these, let's just call it 1.5 man inductors, then the AC power goes into the second filtering capacitor. Then this yellow thing right there, it is actually a MOV. So if there would be a really big pulse coming in through the AC line, then this MOV is supposed to then short circuit and then burn out the fuse instead of burning up the rest of the circuit. So at least they didn't save money there. Then the power goes into this common mode choke, so then both the hot and the neutral wire goes through it. Next to the common mode choke, then there are two of the capacitors which are then mandatory for devices which are put to AC. So this is then put to the hot and to the neutral, and then the middle point should be then grounded, but instead of having a real ground, I mean, they are just relying on this metal turret coming out of the casing of the power supply, and honestly, I hate these cheapo solutions. Right after the common mode choke, then the power is going into two of these Grates rectifier bridges. So yeah, there are two rectifier bridges actually then put together, so they are screwed together. And I don't really understand why haven't they used a single rectifier bridge with a little bit of heatsink on it, but most probably having a heatsink is costing more money than actually putting in one more rectifier. I mean, the power what they save here is really minimal, so I think that the having the solution with the heatsink would be better, and then of course use a higher quality rectifier bridge instead. Next, then this DC power then gonna go to this common mode choke again, and then from the common mode choke then we are going into the power factor correction circuit. So this inductor right here is not a filter inductor, but this is really the inductor for the power factor correction. So it does have active power factor correction built into this power supply, at least something going for it, you know. Here are the field effect transistors, so these two. These are then doing the power factor correction through this coil here, so this is being energized and de-energized as we are crossing the 0 point of the AC voltage. And then here there is a high voltage diode then, which is the recovery diode, through which then the filter capacitor is then being charged. So this way, then via this power factor correction, then they can minimize the rushing current and also produce a lot higher field factor. So meaning that there is not much power being rejected, you know, going backwards towards the wall plug. This really tiny transformator right there is actually the driver transformator giving the signal to the gates of the two field effect transistors, which are responsible for the power factor correction. Before they are going into the capacitor, actually they are here using a thermistor with a negative thermal coefficient, meaning that once this thing is heating up, then actually the resistance gonna drop considerably. So this way they can then minimize the inrush current, and once the power supply is in operation, so this is then getting warm, this thermistor here, then the power lost on this transistor or quatch thermistor is then reduced. Having a thermistor here is, yeah, it's something which is not very nice, because this will always dissipate power. So in most really high conversion efficiency power supplies, actually they either don't use one of these, or they are using a relay and they are then switching off through a relay the thermistor itself after it have done its job. Talking about the main filtering capacitor, it is then a 390 microfarad for 420 volt. Yeah, that's kind of okay. The company who made this is Teapo, however you pronounce it. I don't have very good feelings about this Teapo, especially considering that it is an 85 degrees C capacitor. I mean, let's be honest, most power supplies run really hot. So putting in an 85 degrees C main filter capacitor, it's like really trying to save €1 for a capacitor. I mean, they have to buy this at least in hundreds of thousands of quantities. So it has to be a lot cheaper than how much you pay for them. Yeah, I mean, I find this really one of the corners which you should not cut as a manufacturer. This should be a 105 degrees C capacitor here, but yeah, we got a nice 85 degrees C. After the main bulk filtering capacitor, then we are going now towards the power conversion units. So these are the two transformators which are doing the power conversion. And this small transformer here is the plus 5 volt transformer, meaning that this is always providing plus 5 volt at the output, because that is necessary for all ATX power supplies to provide this voltage, so that then it can be, the whole unit then be switched on through a signal which is then sent through the ATX cable itself. I will show you later what I'm talking about if eventually you don't know what I'm talking about. Then this somewhat larger transformer here is the main power transformer, and this thing is supposed to be a 500 watt unit. I mean, the right question would be, there is like 500 watt. I mean, so this is a 3.5 centimeters times not even 1.5, 1 centimeter, 2 millimeters, and the whole thing is 3.5 centimeter tall. I mean, this is my finger for comparison. This transformator is tiny. I just don't believe it that they can push through 500 watt through this tiny piece of ferrite core. I mean, no way. The frequency what they would need to work to do that would be, I don't know, probably in like the 20 megahertz range or so. I just don't believe it that the field effect transistors what they have here are doing that. So yeah, this 500 watt is probably, like in those old plastic cassettophones, if you owned any, they had written on them like 300 watt PMPO. I would say this is also a 500 watt PMPO unit. You might be able to see, but actually below there is a marking on the printed circuit board of how a real transformator should look like. So as you see, the thing should be a lot larger. So I don't know for which, probably this is a 300 some watt transformator. I would believe that, but the 500 is just with watt. The chopper transformer is then having this roughly plus 310 to up to 330 volt DC being chopped through it via these two field effect transistors here, which are then working in a push-pull configuration. And I don't know how well you can see it, but this is just a flat aluminum there is absolutely no surface area like here for the active power factor correction. At least there is some cooling area to it. I mean, this is really a poor quality job. I'd say that these field effect transistors are probably red hot when this thing is running. The plus 5 volt small transformer is actually not even driven by a field effect transistor. Oh no, that would have been so expensive. Instead, they are using this small 8-pin some specialized power deep package, which is then directly connected to 310 volt DC. I mean, just look at that poor thing. I would say this is ready to then pop whenever something bad happens. So yeah, I mean, yeah, they did an awesome job on trying to save the last dime on this plus 5 volt standby circuit right here. Oh, by the way, talking about the plus 5 volt standby, you would think that the power switch was actually switching the power. So those are the two holes what you see here in the PCB, which are for the power switch. But I can tell you, you couldn't be more wrong. Actually, the power switch, which you would expect in a normal situation, that it is switching the AC power here, the inlet. Oh no, what they are doing is something which I've never ever seen done before. I mean, this is just flabbergasting me. So practically this power switch here is actually switching the plus 310 volt DC, which is then charged into this bulk capacitor, and they are switching that to this 8-pin specialized deep power circuit, which then starts the plus 5 volt standby. And once the 5 volt standby is then charging this capacitor, then they are using this voltage to actually then start the whole circuit. So this is why they have here this transformer here, because once the 5 volt standby here starts up, then on the other side of the printed circuit board you might see, so this is then the whole tiny circuit which is then responsible for the power factor correction and for the switching field effect transistors. So this is then giving the signal to them, and then the plus 5 volt standby is actually giving then the power to this circuit, which then on the other hand starts up then here the field effect transistors. I mean, I'm just, I cannot say anything anymore. Yeah, I mean, wow, I'm just shocked. Seriously, I'm just shocked. Regarding the soldering job itself, since we are anyway already on the solder side of the printed circuit board, so I mean, this is where I desoldered this so-called power connector, but as you see, it just goes to the 8-pin chip directly from the bulk filter capacitor, and this is then just a 0 ohm resistor right there going to the power switch. Anyway, so the soldering job could be definitely better. I mean, it's not very sloppy, but getting there. I see that the components have this glue put below them. You might see this red to brownish glue below the SMD components, which tells me that this board have been wave soldered, which is fine. I mean, that is done quite often. That shouldn't be a problem at all. That is totally fine if it is done properly. And then you might see here on the chip as an example, this leg here have a lot more exposed area, and that is because the board then travels to this direction through the solder wave. So they don't want that the solder is being then stuck on the two legs and short-circuiting those two legs. So this is why they use a larger exposed area. If you eventually want to follow the power, then here you can see also at the bottom. So this is where the power then comes in. This is one of the inductors. The other one, as I showed you, is just jumper. And then we go through the common mode choke. Then here are the two grades bridge rectifiers, then soldered parallel in. Then we are going into the second common mode choke, and then from there then we are going into the two field effect transistors, which are then working through this relatively large inductor coil, then to provide a active power factor correction. And then finally right here we have then this TEAPO, or however you pronounce it, bulk capacitor right here. Then this here is the plus 5 volt standby. This here is actually the separation line, so this is the primary side and here is the secondary side. So as you see, at least they did a minimal job of trying to maximize the creepage between the 230 volt AC side, and this is the DC side here, this is the secondary side. So that's why they cut out a small portion of the PCB. Then they drilled holes at least into the bottom of the PCB to maximize cooling of the transformators, and also to maximize creepage as well. So yeah, at least, you know, they tried it. They made an honest effort on making the PCB decent. On the secondary side then, so this is the primary side on the right hand side, this is the secondary side. So here then they have 1, 2, 3, so they have 4 times 2 double Schottky diodes put in parallel. So one side is here, on the other side then you have parallel the same thing. And I mean, yeah, again, I'm very skeptical about this 80 plus certification, because for that you should definitely do synchronous rectification, meaning that you cannot just get away with you know, double Schottky diodes. No, you actually need to use field effect transistors, which are then synchronized with the transformator, and they are then doing also on the secondary side the switching. So when the transformator is having the right phase, then they switch on, and since the drain source on, or you know, the shortage, the shorthand notation is RDS on of a good field effect transistor is considerably lower than how much power you lose in these Schottky diodes. This is why this synchronous rectification is used at power supplies which produce up to 90, eventually 94% efficiency. This integrated circuit right here on the secondary side is then probably a quad comparator. Normally they use like LM324 or something similar like that, where then they are looking for over voltage correction, and I don't know whether this unit is doing also over current protection, because I don't really see any type of resistors which they could use to actually measure the current. So I would suspect that this is doing only over voltage protection through this comparator right here. And then if there is an over voltage on one of the output rails, then the comparator sends the signal then to this small circuit right there, that it definitely should stop feeding in power to the power supply. On the secondary side, they use actually a quite decent sized inductor right here and also that one there. And these inductors are then serving the purpose of really filtering the DC voltage. So the ripple on the DC voltage is smaller. Furthermore, these are often serving as actual chokes, because otherwise the double diodes would receive really huge inrush currents, because they are charging the filtering capacitors normally only at the peak voltages, and this is why then they are using these ring inductors to then cut off a little bit of this peak amperage. The capacitors for the output voltage filtering are also made by this TAPO, and yeah, I mean, I don't even see a temperature range put on them. Yeah, I would suspect that they are also made for 85 degrees C, most probably. And also, I don't know whether you can see this capacitor right there, and it's no longer happy. If we would make a quote of the big gag of the flying circus, of the Monty Python's flying circus, you know, there is a sentence in the Dirty Hungarian workbook where they say something similar to "my capacitor is exploding with desire." So as you see, the lid is definitely popped on that one. So yeah, that's most probably why my virtualization host and video editing machine is not booting. And that means that I'm gonna definitely replace all these El Cheapo. So yeah, probably the TAPO is El TAPO or El Cheapo filtering capacitors. Then to repair this thing, I actually removed most of the capacitors except the main bulk filtering capacitor, because I didn't find such a relatively high value. I have 220 micro capacitors, but those are definitely then smaller. And actually, as you see on the board, in some of the places I actually started to replace now the capacitors. So then that is the next stage, to replace them all. So then I replaced then all capacitors except the bulk main filtering capacitor. The new capacitors which I put in are made by Yageo, whatever that company is. I mean, they are about 20 cents per piece. But honestly, after doing this overview on this power supply doesn't deserve better than this. In fact, these are 105 degrees C certified, and as you see, they are definitely larger than the original caps which were in, so they are bent a little bit to the side to accommodate for the increased size, because the space is really very small in this power supply. By the way, there is also an additional thing which I haven't noticed, is that look, the power switch, which we know it is exposed to 310 volt DC, actually not even AC, this is DC. Look, this thing is actually then going through here, already the secondary side, and this thing is this cable going through it, and it is fixed by the heatsink. And then of course it is going to switch the 310 volt DC. I mean, this is scary, honestly, this is scary. Now then I'm gonna put this thing together and then test it. After I have then exchanged all the capacitors, I did manage to repair this power supply. It totally works. Nevertheless, I still do not trust it for 24/7 operation in my virtualization server. So this is why then actually I'm looking for replacement power supplies, and I was looking for different manufacturers than Be Quiet, because The price for these units is starting at around 90 euros or such, which is not very cheap. And I must say that the electronics in the other power supplies what I looked at is actually not better than the Be Quiet one. And in comparison, those other power supplies are even using a lower quality cooling fan, and they don't have this nice cage for the cooling fan, which means that the air generates considerably higher amount of noise when it rushes through. As an example, as a potentially cheaper alternative, I have actually bought one of these Corsair VS 550W power supplies, and yeah, I mean, you might want to look at the comparison between the two power supplies if you are in the market and you would like to buy a relatively inexpensive power supply, so that you can see what is my personal opinion about this power supply in comparison to this Be Quiet unit. Many thanks for watching. I hope that you have learned something of what is inside in one of these Be Quiet power supplies, roughly. Of course, this is just the indicative of this particular one. It does not mean that all Be Quiet power supplies are built like this one here. And also, if you would give me eventually some of your personal experiences of what other brands you have used successfully in this like 500 watt range and not more than 80 or 90 euros, then please put your comments in the description below and let me know of what others I may try as well.